Hey folks, welcome back. In this video we're going to go over one worked example to show you how to do problems involving velocity selectors and mass spectrometers as our third application of fields. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get started. In our one and only question here, it says a simplified diagram of a mass spectrometer is shown below. Positive ions of different isotopes are passed through a velocity selector and collimator so that they all have the same velocity. They are then directed into a uniform magnetic field where the ions follow a curved path. The radius of the path will be different for ions with a different mass. So our positive ions from different isotopes come along here, pass through the velocity selector and then into this evacuated chamber. They'll then follow a semicircular curved path until they reach a detector. And it says that the ions pass through the magnetic field acting out of the plane of the diagram. Part A says to explain why the ions follow a curved path to the detector. Well, we could say the magnetic force exerted on the ions due to their movement in the magnetic field produces a centripetal force acting on them. Part B then says to explain why it is important that all of the ions have the same velocity. Well, we could say that the velocity of the ions will affect the radius of their path as well as their mass, so must be the same for all ions. Part C then says to state which of the ions A or B has the greater mass. Justify your answer. So if we look back at our diagram here for the two paths A and B, remember the radius of the semicircular path will be from the middle to the end point or the middle to the starting point, and therefore we can see the ions in path B have a greater radius than those in path A. So we can therefore say that it's B that has the greater mass, and the justification for that is that from the relationship R equals mv over qb, it follows that radius is directly proportional to mass, so the greater the radius of the path, the greater the mass. And we just saw in the diagram that the path of ions B had the greater radius. Lastly, part D says an ion entering the spectrometer's magnetic field has a mass of 6.66 times 10 to the minus 26 kilograms and travels at a speed of 3.0 times 10 to the 7 meters per second. The force acting on the ion is 1.2 times 10 to the minus 9 newtons. Calculate the radius of its path. Well, here we're trying to find radius r. We know the magnetic force is equal to the centripetal force, so F equals 1.2 times 10 to the minus 9 newtons. We're told here that the mass of the ions is 6.66 times 10 to the minus 26 kilograms, and they're travelling at a speed v of 3.0 times 10 to the 7 meters per second. So writing down our equation for centripetal force in terms of mass, linear speed and radius, we have F equals mv squared over r. Substituting in the numbers gives 1.2 times 10 to the minus 9 equals 6.66 times 10 to the minus 26 times 3.0 times 10 to the 7 squared divided by r. And to find r on its own, we can essentially just swap this round with the 1.2 times 10 to the minus 9. And so doing the numerator divided by that in your calculator should give you an answer for r of 0.05 meters. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.